Welcome to the history of mathematics, the queen of the sciences. My name is David Brassu. I'm a mathematician and a teacher, and I have a real passion for the history of mathematics because mathematics is really about ideas. And I think one of the most effective ways of understanding these ideas is to look at how they have developed. Where did they come from? What were people trying to do as they looked at these ideas? How did the ideas arise from many different civilizations and cultures? How did they interact? What were the difficulties that people encountered in developing them? And how do they play out in our world today? I'm also interested in the history of mathematics because I'm interested in it as a teacher. As I try to explain these ideas to my students, I want to look back and be able to motivate the ideas by showing them where they came from, but also, and sometimes even more important, to look back and see where the difficulties have been. Where did people have trouble in coming up with a particular idea? What were the ideas that came naturally, that were easy to find? What were the ideas that were very difficult and took a long time to develop? Those places where the mathematicians and scientists had difficulty with the mathematics, I can expect are going to be places where my own students are going to have difficulty. And it greatly encourages them if I can say, look, this great mathematician, Augustin-Louis Cauchy, the greatest French mathematician of the 1820s, was struggling with this idea. If you're struggling with it too, that's just to be expected. I also enjoy the history of mathematics just because it's full of great stories. We're going to be looking at a lot of interesting people. We're going to be studying people like Leonhard Euler, probably the greatest mathematician who ever lived, who would continue to be incredibly productive even after he was completely blind. We'll look at people who died extremely young. The young Évariste Galois, who would solve one of the most fundamental problems in mathematics at the age of 17 and die before his 21st birthday. We're going to look at the self-taught mathematician Srinivasa Ramanujan. And we're going to see how, despite the obstacles of growing up in southern India without access to much of the mathematics of Western Europe at the time, he was able to get his hand on mathematics textbooks and learn from those and become one of the greatest mathematicians of the 20th century. But before I get into the history of mathematics, I want to back up and look at the topic of this particular lecture, which is, what is mathematics? To me, the essence of mathematics is the abstraction of pattern. What mathematicians do is to look at the world around us and see the patterns that are out there and then abstract those patterns in order to be able to work with them and manipulate them and use them then to tell us more about this world that we see around us. Some of the simple examples of this abstraction of pattern come from numbers. They come from geometry. And most people, when they think of mathematics, they think of number, and to some extent that is appropriate. I hope by the end of these lectures you'll have a much richer sense of the kinds of patterns that mathematicians work with. But the beginning of understanding these patterns really is with number. So we look initially at number simply as a qualifier. We have 5 people. We have 5 loaves of bread. We are looking at 5 stars in the sky. And from that, we abstract the number 5. And that's very useful as we begin to combine objects. If I have 5 people in a room and 3 more people come in, I now have 8 people. If I have 5 loaves of bread and add to those 3 more loaves of bread, I now have 8 loaves of bread. And the fact that we've got, in essence, a 5 and a 3 that combine to become an 8 is something that goes beyond the people or the loaves of bread. It's a mathematical abstraction. And once we take those patterns and begin to abstract them, we can begin to play with them. The same thing happens in geometry. And the basic geometric objects are things like lines and circles and they're really expressing spatial relationships. So we look at 5 stars in the sky and we see that they seem to be in a certain pattern that we describe as a circle. Or we might look at a ring of stones on the ground and we describe that as a circle. Or we might simply have 3 points that we're interested in. There's the tree over there and the house that's here and myself standing somewhere between them, and I consider those 3 points and I begin to think of them as a triangle. And so we get this geometry that comes out of abstracting these patterns. And one of the interesting questions that comes up as you begin to think about these abstractions that mathematicians are working with is, what is the reality behind them? Is 5 something that actually exists? Is a circle, a pure Platonic circle, something that really exists? And of course, I use the adjective Platonic because this gets back to Plato's view that in fact these ideal abstractions really do exist, that there is a reality beyond ourselves that we are tapping into as we make these abstractions. And this gets to a more fundamental question that is often debated by mathematicians and philosophers of mathematics and philosophers of science, and that is whether mathematics is discovered or whether mathematics is created. Are we simply revealing something that is out there as we put together mathematics, or are we creating something? I actually come down between those people who believe that mathematics is discovered and mathematics is created. I am at heart a Platonist. I do believe that there is an ideal world out there that we are trying to understand, that we are trying to tap into. And as we develop these abstractions of patterns that mathematicians work with, we're really trying to explain a deeper reality that is out there. But it is also a very subtle reality. And most mathematicians, most scientists realize that we can never really describe what's out there. What we are doing with mathematics is creating a language, a set of symbols that enables us to work with some aspect of that deeper reality that is out there. But in most cases, we cannot claim that we really fully understand that, we really fully comprehend it. And that's one of the things that makes mathematics so exciting, because as we abstract these patterns, we begin to try to look beyond what we've been working with. What a mathematician does is to take an abstraction of a pattern that she or he sees over here and another pattern that's observed someplace else, and you look for points of similarity between these 2 patterns. And as you overlay the patterns, as you begin to look for these points of similarity, you see that they suggest ways in which the pattern might extend. And so you begin to explore that. Is this really going on? And this is what makes mathematics so very exciting, is this kind of exploration, knowing that there is a world out there that we understand very imperfectly, and we're exploring it in the mathematics, taking what we know, trying to find ways of combining what we know in order to be able to go further into the unknown and to understand that. Now, the patterns of mathematics come from many different sources, and I'll talk about many of these sources through this series of lectures. One of the most important sources comes to us out of commerce and civil administration. And this certainly is where we get basic arithmetic. This is where we get our fundamental operations of addition, subtraction, multiplication, and division, and also simple fractions as well as the whole numbers or integers. And we can see ways in which fractions come up quite naturally. If I have 5 loaves of bread and I want to share them among 3 people, then each person is going to get a loaf of bread and something left over. And to be quite precise, each person, if they are shared equally, will get 1 2/3 loaves of bread. So fractions come in fairly naturally. Commerce and civil administration also give rise to rates. What's the rate at which someone can accomplish a certain job? You want to know how long it will take to build a wall or dig a canal, and so you need to know the rate at which people are working. You want to know what the yield is on a given plot of land, and so you want to know how much barley is produced on each acre. Commerce and civil administration will also be the origins of much of the work in algebra. We're going to see how algebra comes out of these problems in arithmetic, but also how algebra comes out of problems in geometry. And this will be one of the threads in some of the early lectures. Another source of the patterns of mathematics comes from problems of navigation and problems of surveying. So we're trying to do land measurements. This gives rise to geometry, which literally comes from the words geo, earth, and metry or metric measurement. So we are measuring the earth. And geometry then arises from these problems of trying to determine distances, trying to determine areas, trying to determine volumes. As I said, we'll be using geometry to motivate much of what goes on in algebra. And we'll also be using geometry to motivate much of the number theory that I'll be talking about. Number theory is really about understanding the structure of the integers. If I've got an integer like 20, how can I represent it? Can I write it as the sum of two squares? How can I decompose 20 into a product of primes? These kinds of questions are the questions that we're going to see addressed as we look at number theory. A third source of the patterns of mathematics comes to us from astronomy or astrology. And in the ancient world, there really is no clear distinction between astronomy and astrology. And in fact, right up well into the 17th century, people would not make a distinction between these two. You studied the heavens in order to try to understand what was likely to happen on Earth, but you really were doing astronomy. But it was done for astrological purposes. And we're going to see how some of the greatest astronomers also were astrologers, in particular people like Johann Kepler at the very early years of the 1600s, whose work in both astronomy and astrology would lay the foundations for much of the work that would be done in developing the calculus. This distinction between, or lack of distinction between astronomers and astrologers also carries over into mathematicians. And in fact, if you look at the ancient world, or even the medieval world, or even the Renaissance world, the words mathematician, astronomer, and astrologer were used interchangeably. And one of the stories that I like very much is of the Emperor Tiberius, who, it is recorded, banished all mathematicians from the city of Rome. Now, he was not banishing the accountants. He was banishing the astrologers. The astrologers were predicting his downfall, problems for his empire. He didn't like that fact, and so he was banning the astrologers. But to Tiberius, and for many hundreds of years after Tiberius, astronomy, astrology, and mathematics were all bound up in the same package. And largely that's because some of the most important advances in mathematics came directly to us out of astronomy. Because we're trying to understand the patterns of the world around us, and most of the world around us is too messy to be able to pick out these patterns. What we need to do is to take a look at a place where the patterns are much simpler. And astronomy would turn out to be one of those places. By looking at the heavens, we saw these patterns in a much purer form. But it's not just astronomy. We're going to continue that into a general viewpoint of the physical phenomena of the world and how we've pulled patterns from them. We will also be looking at optics, and eventually we're going to be looking at electricity and magnetism, and even the study of subatomic particles, and see how mathematics was influenced and how mathematics often was created from trying to explain these physical phenomena of the world around us. Yet another source of mathematical patterns that will be very important is art and architecture. Especially as we get into the later lectures, we're going to see how the ideas of symmetry would come to play an absolutely fundamental role in the mathematics that would be developed in the 19th and the 20th centuries. And that's one of the reasons why I'm standing in front of a picture of the Lion Court at Alhambra in Granada, because that particular palace is a wonderful example of symmetry in art. And it's actually through the symmetry at Alhambra that many mathematicians have come to a realization of the kinds of patterns that they then could apply to other problems, both in geometry and also in algebra. I want to say a little bit more about number and distance. We've talked about number as abstraction from actual units. So we're counting the number of people or the number of loaves of bread. And sometime in far antiquity, somebody decided to take this idea of number and apply it to distance. And you run into a problem there when you try to apply number to distance, because the difficulty is there is no natural unit when you're looking at distances. If I want to know how far is it from here to there, well, today I might measure that off in feet or meters or yards, but those are simply human constructs. What are we going to use as the unit to measure off distance? And even once we decide what the unit is going to be, there's no reason why the unit we've chosen is really going to be appropriate for the distance that I'm looking at. So if I've got my unit, say a stick, and I'm going to measure off the distance to some point, almost inevitably as I get close to that point, I see that the distance that's left is less than the length of my stick. But I'm not able to take a whole number of sticks and measure that distance. One way of solving this problem of this little piece that's left over is to take my stick and mark it off into smaller intervals. I might mark it off into tenths, or I might follow the Babylonians and mark it off into 60 small pieces. Or I might follow the Romans and mark it off into 12 small pieces. This is where we get our foot divided into 12 inches. And I'm now going to take these smaller pieces and try to measure off the remaining distance. But almost inevitably, the smaller pieces are not going to measure the remaining distance exactly, and so I'm going to need smaller units still. Take each of those inches, take each of those small pieces, and subdivide them. And as I do that, again, it won't exactly match. And eventually the scientists, or in the case of early mathematics, the bureaucrats, began to realize that in fact this was a process that would never end. And now the question is, does it make sense to talk about the distance between here to there as a number if we can never express that number exactly, if the best we can do is get these approximations using smaller and smaller units? This is a question that the Greek mathematicians would really wrestle with, but we're also going to see it in the Babylonian mathematics of 4,000 years ago. Trying to apply number to time introduces other problems that are going to be very important to our story, because unlike distance, where there is no natural unit, when I look at time, we've got too many units. We've got the day, we've got the lunar month, and we've got the solar year. And each of these units is incommensurable with the other. You cannot measure off a lunar month in a precise number of days. It's going to be a number of days plus a bit left over. And you cannot measure off a solar year in an exact number of lunar months or an exact number of days. Whichever of these two units you use, there's going to be a little bit left over. And as you subdivide these units, there's always going to be a little bit left over. But even more importantly, what's happening is we've got different units traveling in different cycles. And this would present fascinating problems for mathematicians to wrestle with, is how to figure out when all of these cycles would line up. A very important question in astronomy and astrology as people look not just at the cycles of the day, the month, and the year, but also the period that it would take Mars to circle the Earth, or the time it would take Venus to circle the Earth, or the time it would take Saturn to circle the Earth, and then trying to find out when different planets would actually be in alignment in the future. As we explore this question of the nature of mathematics, it's going to be very useful to refer to two papers that I'd like to talk about now, the first of which was written by the physicist Eugene Wigner, who taught at Princeton University. And he published the paper in 1960. It's called The Unreasonable Effectiveness of Mathematics in the Natural Sciences. And one of the things that Wigner observed as a physicist was that physicists look at the world around them and they try to understand the patterns that they see, and then they turn to mathematics. And they ask, are there similar kinds of patterns that the mathematicians have been working with? Can I take this pattern in mathematics and apply it to the physical phenomena? And Wigner remarked that, amazingly, most of the time when physicists see a pattern in the natural world and they pick up a pattern from mathematics, that pattern in mathematics actually fits what's going on in the natural world with amazing accuracy. And not just amazing accuracy, it also often has excess content. It is possible to take that mathematical model and see beyond what we were trying to explain. So not only does the mathematical model enable us to do the predictions of what we already saw, it suggests a deeper reality that is out there. I will return to this theme periodically as I talk about the work of Newton, and also especially in the second to last lecture, when I'm going to show how mathematics really does represent the ultimate physical reality, showing us things that we never would have expected without the mathematical models. And Wigner asks the question, why is mathematics so good at this? He defines mathematics as the science of skillful operations with concepts and rules invented just for this purpose. Now that suggests that there's an arbitrary nature to mathematics that I don't quite buy. I do not believe that mathematicians just sit at their desks and try to think up interesting patterns that they can play around with. As I said, mathematicians really get their ideas for the patterns that they will study by looking at the world around them. And so, in some respects, we should not be surprised that if we look at the world around us and we extract a pattern and then we try to apply this pattern to the world around us, it often will fit. But what is surprising is that the patterns that are pulled out of one area, so for example, we're going to see how astronomical phenomena gave rise to the trigonometric functions, we can then take those trigonometric functions and apply them to something that seems to be totally unrelated to the heavens, namely a vibrating string, and see that exactly these trigonometric functions that came out of our study of astronomy are going to be applicable to problems in mechanics, problems of vibrating strings, and actually eventually applicable to problems like heat flow and electricity and magnetism. There was a second article that I want to talk about. This is really a response to Wigner's article. It was written by Richard Hamming in 1980, and it's called simply The Unreasonable Effectiveness of Mathematics. Richard Hamming was a very prominent applied mathematician. He worked at Bell Labs, and he did a lot of work in signal processing. And he was also interested in this question of why mathematics seems to be so useful, so effective. And he did raise that point that I did, that after all, mathematics is extracted from the world around us, so we shouldn't be too surprised that it's applicable when we try to apply it back to the world. He was actually less surprised, though, that it could be applied to other areas than I am. But I want to raise Hamming's article because he does a nice job of clarifying what mathematics is. He describes the four faces of mathematics. And the first two I've already talked about. The first face of mathematics is number. The second face of mathematics is geometry. The third face of mathematics is close reasoning. And this is extremely important because, as I said, as we're looking at mathematics, we're taking these patterns, we're overlaying patterns, and very often we're extracting patterns from the overlay of patterns. And as we build these abstractions of the patterns that we saw, they create new patterns and we abstract from them. And mathematicians are often working with abstractions of abstractions of abstractions of abstractions. And to keep track of what's going on and to really have a reliance on the results that you get, to have some confidence that you really have found something that really is there, that really will be useful, you need tools in order to keep track of these abstractions of abstractions and how they work together, and what are the legitimate conclusions that can be drawn and what are not the legitimate conclusions. Now, one of the ways of doing this is through formal logic, the logic that was developed in Greece, that comes to us from the Greek mathematical tradition. But I like the fact that Hamming uses the words close reasoning rather than logic, because I think the picture is much broader than just the kind of formal logic that we know from Euclid's Elements, the Euclidean geometry. As we look at many different cultures, many civilizations, and the way that they have developed mathematics, we're going to see that they came up with different ways of maintaining this close reasoning. It did not have to be the kind of formal logic developed in Greece. And the fourth of the faces that Hamming talks about is artistic taste, and I really like this, because there is something about mathematics that is very aesthetically appealing. And as we're looking for these patterns, there almost inevitably has to be an aesthetic appeal if we're on the right track. When we see the kinds of symmetries that we want, when we see these kinds of patterns coming together and just clicking perfectly, perhaps in an unexpected way, but in a very satisfying way, that's what tells us that we are working with real mathematics and with important mathematics. And it's very difficult to define this aha moment when things come together, but it's incredibly exciting when it does. And there is this real feeling of the need for artistic taste and the artistic appreciation that comes from it. I believe that mathematics is far less arbitrary than Wigner talked about it. I believe that it's much more surprising than Hamming claimed it was. And I hope to be able to communicate that to you in this series of lectures. My lectures are going to cover 4,000 years of the history of mathematics. And there's no way I can do this in any kind of detail. I want to bring you right up to the 21st century. I want to share with you some of the exciting things that mathematicians are doing today. And so I'm going to have to treat much of this history of mathematics in a very superficial way. But I hope to be able to communicate some of the really big ideas. In looking at how to structure these 4,000 years going all the way back to the ancient Babylonians and Egyptians, I decided that the real pivot point occurs in the 17th century. And that's when we get 5 different threads coming together. And the threads are algebra and geometry and astronomy and mechanics, the way that physical systems interact with each other. And then the last of these is going to be the mathematics of motion. And we're going to see how different ancient civilizations developed these threads until by around the year 1600 they come together. We're going to see these threads coming out of the ancient Mesopotamians, the Egyptians, the Greeks. We're going to go to South Asia and see how the Indian mathematicians of the first millennium AD developed the ideas. We're going to turn to China and see how these ideas were further developed there, how the Islamic world took all of the different threads of mathematics that had been developed up until that time and really pushed them much, much further and laid the foundation on which Western Europe would be able to pick up these threads and continue to develop them, until by 1600 they were ready to be woven together. And I'm actually going to spend 5 entire lectures just on the 17th century because this is such an exciting time as these mathematical ideas came to maturity and people began to see how they could interact, how you could weave them together. And the great master of weaving these threads together was Isaac Newton. He saw how to combine them in new and very important ways. And Newton's mathematical principles of natural philosophy, not truly a work of mathematics, it's really a work of physics or of science. It is explaining celestial mechanics. But in it, he shows how all of the mathematics that had been developed up to that point could be brought together and united into very exciting new mathematical ideas. And then beyond the 17th century, I will follow the development of mathematics, treating it very superficially now, just touching on a few of the points that I find most interesting, some of the people that I enjoy talking about the most. So the mathematics after the 17th century is going to be extremely personal. I'm going to share with you my own enthusiasms, my own excitements, and hopefully bring you up to the point where you have some idea of why it is so exciting to be a mathematician today.